Memory prices have roughly doubled since early 2025. Micron, one of the three companies that make nearly all the world's RAM, is sold out for 2026. Data centers now consume about 70% of all memory chips produced worldwide. The rest of us are standing in line. There is a specific reason this is happening. It is not just that AI uses a lot of memory in general. One particular architecture tipped the balance: mixture of experts. MOE decouples two things that used to travel together: total parameters, how much the model can store, and active parameters, how much compute each token actually burns. A dense model runs every parameter for every token. MOE gives the model thousands of expert feed-forward blocks, then picks only a small handful to activate per token. The capacity gets big, the per-token bill stays small. The catch is where those inactive experts live. They still have to sit somewhere, ready to be woken up. That somewhere is memory. And memory is exactly what the world is running out of. To see why, you have to understand how routing works. In a normal transformer, every token passes through the same feed-forward layer. In an MOE transformer, that feed-forward layer is replaced by a shelf of experts, plus a router. The router is a small learned projection. For each token at each MOE layer, it scores every expert, picks the top few, and sends the token to only those. This happens token by token, layer by layer. The same word in a different position or the next word in the sentence may route to completely different experts. There is no easy preload. You cannot just page the math expert to disk and leave the code expert in RAM, because the router does not know what the next token will be until it sees it. The word expert contributes to the confusion. People picture named specialists: the math guy, the code guy, the safety guy. The reality is messier. Experts are learned feed-forward blocks. Training pushes them into different roles through routing pressure and gradient updates, but the roles are not clean, human-labeled jobs. They are more like tools that got worn into different shapes through repeated use on different kinds of work. This is also why you cannot just think of the router as a dispatcher who knows in advance where to send things. The routing decision is made fresh for every token, at every layer, based on the hidden state of that token at that moment. The system has to hold all the tools close enough to reach. The original MOE idea aimed for specialization, not scale. In 1991, Geoffrey Hinton and three collaborators published Adaptive Mixtures of Local Experts. They showed that separate small networks could divide a task, vowel discrimination in their demo, into subtasks. A gating network learned how much to trust each local expert. That is the family resemblance. Pieces specialize. A gate decides how to mix them. But the modern version changed the motivation. Noam Shazia and a Google team made that clear in their 2017 paper. The title was Outrageously Large Neural Networks. The same Shazia Google later spent $2.7 billion to rehire after he left to start Character.ai. The paper's opening line: the capacity of a neural network to absorb information is limited by its number of parameters. The insight was that you could own thousands of experts, but only activate a handful. More capacity without proportional compute. That is the modern MOE bargain, and it is a bargain that costs memory. Mixtral is where a lot of developers first saw this trade-off clearly. Mistral took a model shaped like Mistral 7B and replaced the feed-forward blocks with 8 experts. For every token, at every MOE layer, the router picks 2. Mixtral has about 47 billion total parameters, but each token only uses about 13 billion active ones. So it can draw from a much larger weight bank than a 13 billion parameter dense model, while paying compute closer to that smaller model. But all 47 billion parameters still need to be loaded. MOE gives you a bigger parts cabinet. It does not make the cabinet lighter. That bigger cabinet has a consequence you can feel on real hardware. Jeremy Howard put it bluntly on Twitter: MOE is strictly worse for people using discrete GPUs like a 3090, and pretty good for unified memory machines like Macs. The reason is boring and important. A 3090 has 24 gigabytes of fast memory. A Mac with unified memory can push past 128. MOE needs all those inactive experts loaded somewhere. The Mac has room. The 3090 does not. Active parameters tell you compute. Total parameters tell you memory. For MOE, memory is the binding constraint. DeepSeek attacked the memory problem from inside the architecture. DeepSeek MOE split experts into smaller, finer-grained pieces, then activated more of those smaller pieces. The router gets more flexible combinations without every expert carrying the full load. It also added shared experts, always-on blocks that handle common knowledge, so the rooted experts do not all waste capacity relearning the same basics. In plain terms, keep a few general tools on the bench all the time and let the specialized drawers actually specialize. It makes the memory you have go further. DeepSeek V2 showed the payoff. 236 billion total parameters, 21 billion active, and the company claimed stronger performance than its older 67 billion dense model while cutting training cost by 42% and boosting generation throughput nearly 6 times. And the other labs are making the same bet. Kimi K2, 1 trillion total, 32 billion active. Qwen 3, 235 billion total, 22 billion active. Llama 4 Maverick, about 400 billion total, 17 billion active. These are not just big models, they are bets that the world will keep finding ways to feed them memory. The problem is the world is struggling to keep up. GPUs get faster every generation. Memory bandwidth has not. A modern GPU spends a significant fraction of its time waiting for weights to arrive before it can do any math. One analyst described it as the processor twiddling its thumbs. Every new generation of MOE model makes this harder to ignore. The systems people are now working on this from the other end. TryDAO posted that MOE layers take the most time and memory in modern models, and top K routing alone can eat 15 to 20% of a layer. VLLM is building elastic expert parallelism, so a running MOE deployment can redistribute experts across GPUs without restarting. Perplexity published custom MOE communication kernels for trillion-parameter models across cloud nodes. The frontier is no longer whether experts can specialize, it is whether you can move tokens between GPUs fast enough that the plumbing does not eat the savings. Some teams are trying to solve the memory problem by changing where the weights live. Apple published a paper in 2023 called LLM in a Flash. The idea is to keep model weights on the SSD and stream them into RAM on demand instead of preloading everything. They use techniques called windowing and row-column bundling to predict which weights will be needed next and read them in bigger, more efficient chunks. The result? You can run a model up to twice the size of your available RAM. This works better for MOE than it would for a dense model because MOE naturally only needs a fraction of weights per token. You can keep the dense parts and the active experts in RAM and let the inactive experts live on flash. A developer recently got a 397 billion parameter Qwen MOE model running on a MacBook Pro with 48 gigabytes of unified memory at a few tokens per second using this approach. There is a sharp counterpoint worth knowing about. A 2025 paper titled SSD Offloading for LLM Mixture of Experts Weights Considered Harmful in Energy Efficiency ran the numbers. Offloading MOE weights to an SSD can increase per token energy consumption by up to 12 times compared to keeping everything in HBM. The SSD's read energy per bit is substantially higher than DRAM. Prefetching can hide the latency, but it cannot hide the energy cost. So the flash approach solves a capacity problem and creates an efficiency problem. This is the MOE story in miniature. Every move trades one constraint for another. Other approaches are emerging. A system called Flash MOE uses a lightweight machine-learned cache. It predicts which experts will be used soon and keeps those in RAM, while the rest live on SSD. Llama.cpp has an experimental branch that pages missing experts from disk on demand, keeping only a small pool of expert slots in memory. These are not solved problems. They are early attempts to answer the question MOE keeps asking. How do you give a model more capacity than it can afford to store? So here is the arc. MOE began as an idea about specialization, small networks learning different subtasks. Shazir and the Google team turned it into a scaling trick, more parameters without proportionally more compute. But the bargain had a hidden cost, All those extra parameters still need memory. Now that cost is visible. Micron is sold out. Memory prices have doubled. Data centers are consuming 70% of the world's chips. The architecture that was supposed to make AI cheaper ended up making memory the most contested resource in computing. Solutions are being explored: flash streaming, expert caching, smarter offloading. But for now, MOE remains what it has always been: a bet that you can split capacity from compute and that the world will build enough memory to keep up.